Okay, thank you. I'm Yuqi, a fourth-year PhD candidate at University of Virginia. Today, I will introduce our paper, Adaptive Learning Priority OS Scheduler for Service Functions. This work is collaborated with Ruizhe and Haoliang and supervised by Songqing, Chen, and Cheng. So firstly, let me introduce service computing. Service computing enables a new way of building and scaling applications by allowing users to write fine-grained call functions. It introduces a new execution module, function as service (FaaS), which using the call functions as a basic deployment unit. It has three main benefits. Firstly, users are able to run the application virtually and any scale on the cloud resource. Secondly, they are only charged by the amount of results they actually use. Secondly, they can save lots of development and operating costs due to such as the resource provisioning and the backend management. FaaS solutions are growing in popularity and finding their way into commercial clouds, such as AWS Lambda, Azure Functions, Google Cloud Compute, and Alibaba Cloud Compute. In a typical workflow, users will write and define their function and upload the function to the cloud providers. Cloud providers will deploy several functions in the cloud. And once the function is invoked, cloud provider will fully representative to dispatch this task to the functions. However, when execute those function tests, they will finally operate by the local operating system. Therefore, the performance of local operating system scheduler is also essential for the end-to-end performance of serverless computing. However, the current scheduler has its own limitation. Let's first look at the CFS, which stands for the Complete File Scheduler. It's well-known to personally share the time size to the function test in the system. However, and it's also the default Linux scheduler. And in the deployment, it has a local balancer which will dispatch the tasks to different independent workers in the operating system. And each independent worker will have roughly same load. And in the operating system, the independent worker is CPU. CFS will maintain a red-black tree in each CPU and sort all the tasks in the system by the virtual runtime. The virtual runtime system is initial for the CFS. And actually, CFS will gradually pick the text with minimal virtual runtime to run as the next scheduling as a surrounding entity. Let's see how it works in a simple example. So in the red figures, the x dimension represents the timeline, and the y dimension is the CPU resource. And in this simple workload, we have 4 jobs. Among those, job 1 and job 2 are short jobs, and job 3 and 4 are long jobs. So CFS will determine the context switch and update virtual runtime, and then find the next task when doing each scheduling decisions. Therefore, we can see because the CFS will gradually pick the text with minimal virtual runtime. Therefore, it can guarantee the fairness. However, does this fairness could also introduce optimal end-to-end performance for service functions? Let's look at an easy example. So let's see the CPU 2. So at the beginning of the CPU, at the beginning of this workload, CFS will determine which job to run first, job 2 or job 4. Because at this time, the job 2 and job 4 have the same virtual runtime. Therefore, CFS just randomly pick one of them. However, as we know, the job 2 is much shorter than job 4. Therefore, the optimal solution is to run job 2 here. Therefore, we can know that because CPU has no awareness about the actual execution time for each function test, it could achieve suboptimal decisions. In another example, when the job 1 just completes its first time slice, The CFS will do context switch because because the job 3 has a smaller virtual runtime. However, as we know, the job 2 is near to completion. Therefore, a better strategy is to grant another time size to the job 1 to let it run to completion. Therefore, we got the implication CFS lack of application workloads intelligence. Therefore, it will cause the suboptimal schedule decisions. And the approach to mitigate this problem is to approximating the SRPT. However, it also has some limitations. SRT stands for the shortest remaining processing time, and it proves optimal for average performance. However, it's well known in practical in the online scaling because it gradually picks the task with minimum virtual runtime. Therefore, it's assumed that it should have exact full knowledge about the function execution time. And it will also cause the starvation for long-term functions. And due to this implication, we want to propose a new scalar that we want to approximate SRPT to have a better end-to-end performance compared with CFS. However, we want our scalar to be more flexible, therefore can avoid the resource starvation for long jobs. Then let me introduce our ALPS design and its implementation. So first, let's look at the bird view of ALPS design. In ALPS design, we have two components, one component in the user space and the other in the kernel. In the user space, we will learn the scaling behaviors from the FaaS workloads, and we will abstract this behavior as a scaling policy. And then we will rely on eBPF to transform those learning behavior to the kernel. And we actually will hook some critical paths in the kernel. Therefore, we can actually modify the behavior of the kernel scheduling. And on the other hand, the kernel will send feedback to the user space to improve the performance on the learning policy. So, as a summary, ALPS propose a novel OS scalar architecture that decouples the user space front end and the kernel space back end. From the policy perspective, we propose two types of scaling policy: time size policy and task ordering policy. The time size policy will determine how long a time size should be assigned to different functions. And in the task ordering policy, you should determine the execution order for different function types. And from the mechanism view, we will use eBPF to communicate the user space and the kernel space. Then let's see ALPS design in detail. So as mentioned, the ALPS has two components, the front end and the back end. Front end will sit in the user space, and the front end will sit in the kernel space. Firstly, front end will select past function traces by sliding window, and because the front end will select the most recent traces, therefore it can characterize the most relative information from the FaaS workload. Then based on those past function traces, we will learn the scaling. Firstly, we will do a SRPT simulation. It basically simulates the SRPT decisions based on the current workload characteristics. Therefore, those decisions can be used for us to learn how the SRPT will schedule offline. And then we will learn the scaling policy. As mentioned, there are two types of policy. Then we will practically upload the scaling policy to the eBPF map. It's noted that those eBPF maps can be read and write for both user space and kernel space. So that's how we communicate with the front end and the back end. Then practically, we also will deploy these scaling policies. Basically, we will define several hooks in the critical path of the Linux kernel, and our learning scalar will modify the original behavior of the of the CFS in the kernel. At the feedback, ALPS backend will profile the actual CPU time to front end to help improve the learning performance. Then let's talk about the SRP simulation. As mentioned, we will select the pass function trees by sliding window. This sliding window could conclude the workload statistics. For example, the function UID, arrival time, termination time, and the CPU time. It's noted that we develop a new system called ALPS executive. This new executive call do nothing, but allow users to transfer the function UID from user space to kernel space. Therefore, eBPF maps and functions can identify the function UID in the kernel to apply customized learning policies for different types of function. And the CPU time is also profiled by the profiler developed by the eBPF. For simulation, we actually build a priority queue to sort all the offline tasks from short job to long jobs. It's noted that the execution time from those function tasks is unknown on the online scheduling in the CFS. However, because this simulation is offline simulation, therefore all the execution time is known for us. The SRPT profile will conclude the waiting time, execution time, and time size for different functions. Then we're using machine learning-based regression to learn our scheduling policy, the time size policy, and the test owning policy. To understand how we learn and deploy those policies, we should first understand how CFS works in the kernel. So firstly, ticket interrupt or task preemption will invoke the CFS main schedule function in the kernel. The schedule function will initially determine which task to run next. To achieve this, the CFS will query the arbitrary for each CPU. And because the arbitrary will sort all the tasks by the virtual time, therefore we have those equations. Task A will have high priority than task B, and will high priority than task C. Then let's see how our ALPS time size policy could modify these logics. So as mentioned, we were using the SRPT simulation profiles to learn our policy. The policy is essentially the expect time size upper bound for different function types. For example, the task A upper bound time policy is 40 milliseconds, and task B is 8 milliseconds. Those values, those upper bound values, will store in the eBPF maps, and the kernel will deploy those tasks by reading the eBPF value of eBPF maps. Basically, for each scaling decision, we compare the current time size, the task already run, and with the upper bound time size read by the eBPF maps. If the current time size is greater than the upper bound values, we will go to the CFI branch that picks the task with minimal virtual runtime. And if the current time size is less than the upper bound, we will see that we want to grant another time size to those tasks. Therefore, we go to the ALPS branch that grants additional time size to the current test. Then let's see how the ALPS test ordering policy works. So similarly, we learned the test ordering policy from simulation profiles. We basically will learn the expect ALPS test priority for different functions. For example, in the ALPS test priority, the priority of task A is 2, and the task B is 1. We want our new ALPS defined priority should override the CFS virtual runtime. To achieve that, similarly, we're using the eBPF maps to deploy those policies. And as a result, instead of sort all the tasks by the virtual runtime, we will sort them by the ALPS priority. In this example, the test B will have a priority of 1 smaller than test A with priority of 2. Therefore, we say test B is smaller than the test A. But it's noted that when we compare test A and test C, they have same ALPS priority. Therefore, we will reuse the CFS virtual runtime mechanism. Finally, let's see our evaluation. We deploy the ALPS in the OpenLambda and using the Docker as a FaaS worker. We modify 100 lines of code in OpenLambda and about 2 lines of code in the Docker. We run experiment in a large bare metal, and we run experiment based on two production workload traces, the Huawei cloud function traces and the other function traces. Then let's see the end-to-end performance of other workloads. In these two figures, left-hand side figures represent the end-to-end performance for short functions, and the right figure shows performance of long functions. In both figures, X dimension represents the execution durations by milliseconds, and Y dimension represents its cumulative density functions. So firstly, we could easily see that ALPS could achieve shorter execution time compared with CFS for both short and long-term functions. Also, when we compare the tail latency for the CFS and ALPS, we could see the ALPS could also achieve a shorter tail latency, as shown in the right block. Then let's see the end-to-end performance to Huawei workloads. In this workload, X dimension represents the performance percentiles. So firstly, we can see at the 40 percentiles, the CFS can achieve about 50% improvement to CFS for short jobs, and can achieve 5 times improvement for long jobs. And it's also see that ALPS could outperform CFS across all function execution duration percentiles. And in conclusion, we could see that ALPS proposes to learn fast workloads intelligence from user space by the offline SRPT simulation. And we build a prototype to communicate the user space front end and back end by customized eTPF functions and maps. And evaluation shows that ALPS could actually improve the performance of CFS for both short functions and long functions. So thank you.